it's Loren from D Squared Consulting, and on today's D Squared Classroom video, we're going to continue our discussion on material properties. So let's get to it. So last video we talked about stress-strain diagram. So just a little recap. Stress is the force that a material can withstand, or essentially how hard your material is being pulled. And strain is the change in length of the material. So essentially how much is your material stretching when you're pulling it. A typical stress-strain diagram looks something like this. We have a linear region which shows elastic deformation, and that means that when you stop pulling the material, it snaps back into place. And then we have the curved region of the diagram, which means plastic deformation. And at this point, you start getting permanent damage. So if you were to let go, it's not going to go back to its original position. So when we put it in our tensile testing machine, you'll see it stretch and stretch and stretch, and then eventually you'll see a crack form until you have complete fracture and you have two pieces left in the tensile testing machine. So this diagram that we're looking at is typical for a metal sort of material. Metals tend to go through all of these phases. You have the linear region, the curved region, until fracture. But not all materials behave this way. So a different material is a ceramic. And what you'll see with a ceramic is a short, sharp, linear portion, and then fracture. So essentially what this means is that the ceramic materials, they can withstand a lot of stress. You put a lot of force on it and they're strong materials. They can withstand it, but they're not going to stretch that much. Think about brick. Think about clay. Can you stretch brick or clay? You can't. But we know that this is strong material. Like you have bricks on the side of your house sometimes. So bricks are strong. So in these ceramics, what's going to happen is if you were to put a ceramic in a tensile testing machine, you're going to pull, and you're not going to see a lot of deformation. You're not going to see a lot of stretching. And then all of a sudden it's going to crack. You're going to go from fully attached to fully cracked. So on the other extreme, we have polymers, and polymers have a very curved tensile test stress strain diagram. So essentially, these kind of have the opposite characteristics of ceramics. So they don't go very high up on the stress axis, which means they're not very strong of materials. But if you look, they go very far on the strain axis, which means that these materials show a lot of deformation. If you pull them, they're stretching and stretching and stretching a lot. So think about pulling silly putty in a tensile testing machine. If you were to pull it, you're going to be able to get a lot of stretch. You can pull silly putty for a while before it ends up breaking. And what you'll see is that the middle will start to decrease in width. So you'll start to get like a shorter and shorter material in the center of where you're pulling it until eventually your material just breaks. So let's kind of solidify our thinking about material properties and the different types of fracture with thinking through an example. So if we have a big, heavy guy, maybe think about Hagrid from Harry Potter, and he's tired and he wants to sit down on a chair, and he chooses a chair made of metal, he might cause the chair to dip down a bit before it eventually breaks. So this is kind of showing the strength of metal because it's not breaking right away, but also the deformation and the stretch the material can have. So the metal is dipping down in the center, kind of showing that deformation before it breaks. On the other hand, if he were to choose a ceramic chair, the ceramic might be able to hold him because ceramics are considered strong material. But let's just say his big dog wants to get up with him and jumps on the chair, and all of a sudden now there's too much weight. This ceramic is going to break very suddenly. We're not going to see that deformation or that dip down in the center that we did with the metal because ceramics don't really have that curved region of the diagram. We're going to go from it being held up to then being completely broken. And then we also have a polymer. So think about a very, very stretchy seat. If he were to sit down, his behind might be all down on the ground because that's how stretchy the material is. And then if you have a thick material that could withstand a lot of force, Hagrid might even get slingshot into the air because that's how stretchy certain polymers can be. So this example just shows that different materials can be useful for different applications. If you want a strong material, you might choose a different material than one if you wanted a lot of stretch. So as engineers and we're making products, we use different types of materials all the time for different applications. We have to consider the strength of the material, how much it will deform, and how it will fracture. Because if you don't consider these, you might end up with a product that fails. But if you keep these in mind and you pick your materials wisely, you could have a very successful product.